Sure. Yeah, I'll finish. Not to worry.
All right. Welcome everyone to the second week of this 2D workshop. So a lot of new participants. So welcome to all of you. And I'm Arun Paramekanti. I'm one of the co-organizers and will be chairing the session. So we have two talks in the session. And the first talk by Abhay Pasupathy and the second by Manish Jain. So before we begin, I just had a quick announcement. So during the afternoon tea break, there'll be a photograph taken for the conference photograph. More details, I think, will be given by, I think one of the other organizers is in charge, so they'll kind of tell you more about it probably in the session after lunch. So without further delay, let's begin. So with the first talk by Abhay Pasupathy from Colombia.
Okay, thanks, Arun. Thank you to you and the other organizers for having me here. It's always a pleasure to be back in my hometown. And today it's not raining, so that's good. Hey, Shahal, I see you so many times this summer. Okay. So for those of you who don't know me, I primarily work at Columbia University, but I have a second master to pay the bills, which is Brookhaven National Lab. Okay, I'm going to tell you about work that we've been working on for about 5 years, which is, I hope fits within the theme of this conference. It's at engineered quantum systems. And this is very much engineered after a certain way, two layers of twisted tungsten diselenide. Tungsten diselenide is a famous monolayer semiconductor. Let me first start by acknowledging the people who did this work. So this work was actually started by one of my graduate students who's now moved on, Augusto. And it's an interesting case of why one should go to a conference and hear random things. So the way we got into this was sometime late in 2018, we went to a conference. This was shortly after the twisted bilayer graphene, and Pablo was there and Philip Kim and other people. And I was talking to Philip, and I said, Philip, what are you doing in this field? And Philip said, well, we are measuring twisted WSe2. And I said, well, did you find anything interesting? He said, well, it seems to be a superconductor. And I asked him, oh, well, what's TC? He said, maybe 10 Kelvin, maybe 1 Kelvin. I said, what is this? And Augusto was standing next to me, and he said, this sounds very suspicious. I'm going to go home and start making these samples. Okay, so that's how he got into it. It turned out to be a complete rumor. None of Philip's samples are superconducting. In fact, right now I'll show you some evidence for superconductivity, which is actually very recent. Anyway, so the way Augusto got into it was he gathered a student from Corey Dean's lab. This is N Min, who's also moved on now. So Augusto at the time was not very good with all of this tearing and all of this stuff, which is now very popular. But there was a postdoc who was a joint postdoc in our Morsec Center, Lei Wang, who's also now moved on. And Augusto sort of grabbed these two guys, N Min and Lei. And the first set of work was sort of the three of them. Since then, the sort of more recent work, people from my group, Larry and Aya. I'll also talk most recently about superconductivity work, which happened sort of by accident. This is one of Corey Dean's students, Inji. And I work very closely with Corey and Jim Hone. They are the people who teach me all this 2D stuff. And then there's hexagonal boron nitride, of course. I'm sure many of you know these friends of everybody. And then a lot of theory, especially Andy Millis and his group, but also Angel Rubio and his group. Okay, so let me tell you, I assume you might have heard some of this earlier in the conference, or I'm sure earlier before. This is sort of a popular field. But let me get to the basic physics of what it is that we're trying to do. We are trying to create systems where we quench the kinetic energy of the electrons. And so the basic idea is very old, goes back to many different systems. The idea is you take a free particle, which has some quadratic dispersion in 2 dimensions. This has a flat density of states. And you apply a superlattice potential. The superlattice potential has some periodicity in real space and some periodicity in reciprocal space. And that breaks up this original band, which has a large bandwidth, into little mini bands, and these little mini bands can have an arbitrarily small bandwidth depending upon how big you make this superlattice. Now, for practical reasons, you want the bandwidth of this superlattice to be not too small, If it's too small and you have disorder in your system, then you can have all kinds of localization effects. So you want it, in the case of TMDs, to be on the order of tens of MeV. And if you work that out into real space and ask what the superlattice potential should be, it should be on the order of 5 to 10 nanometers. That's the typical length scale we're talking about. Okay, and the way this is done, this goes back to, I believe, Emmanuel, who's right there, who came up with this very clever way of doing business, which is to take a sheet, which is a two-dimensional material, tear it into two pieces, twist one relative to the other, and put it on top of each other. This is called the tear and stack method. And there have been many sort of iterations of this over the years since, I think, now 2015, that's when he first did it. But the same basic idea is applied in each case. And all the physics that I'm going to tell you about refers to the case where the chemical potential is within this lowest subband. So the chemical potential is lying somewhere within this guy. And so for all practical purposes, you can ignore a lot of these other subbands which lie at higher energy. And you can imagine what life is like in a single spinful, in the case of WSe2, single spinful subband, which you can control the doping, and you can also control the bandwidth, as I'll explain in just a second. And for almost everything, this kind of description is reasonable. Of course, if you're dealing with topological properties, then you have to worry about multiple bands. But in this talk, I'll not be discussing any topology. And in this system is actually a really nice platform for engineering. So you can do many different things to tune this system. So simplest thing you can do is you can choose different types of materials. The material I'll talk about is twisted tungsten diselenide. But there's work on tungsten diselenide, on tungsten disulfide. There's tungsten diselenide on molytelluride, molytelluride on molytelluride. And if you've been following this field, there have been sort of many beautiful experimental discoveries over the past few years, Wigner crystals, the anomalous integer quantum Hall effect, and most recently, the anomalous fractional quantum Hall effect. All of these things have been discovered in this materials platform. Now, once you've picked a particular material, you still have a lot of tuning parameters that you can play with. You can play with the twist angle. So the twist angle sets the wavelength of the superlattice in real space. And the smaller the twist angle, the larger the wavelength in real space, and the smaller the wavelength in reciprocal space. You also have two gates in all of these devices. So if you have a bilayer, you can put a gate on top and a gate on the bottom. If you apply the same voltage to both the gates, then you tune the density of electrons on this. And if you apply equal and opposite voltages to the two gates, then you end up applying just an electric field. And as I'll show you, the electric field in our system controls the bandwidth of the system. Okay? And finally, one thing that we've sort of by accident gotten to recently is you can also control dielectric screening in this system. So you have a bilayer system, and the bilayer system is close to a gate. And if you bring this gate very, very close to the bilayer system, then effectively you screen the long-range part of the Coulomb interaction. So this is another degree of freedom that you can play with. Okay, so I'll keep an eye on time. I'll make sure I won't go late. But I wanted to sort of review all of the work that we've been doing since our original work. So I'll talk about 1, 2, 3, 4, 5 different things. Out of these 5 things, I'll try to be fairly quick about 1, 2, and 3, these first 3 things. This is sort of in the nature of background. And I'll try to spend a little bit more time on the most recent results, which is from this year. Okay, okay, so let's start with the first part of the story, which is what happens when you make the sample. What's the most obvious thing that you see in these samples? And I should also mention that these particular samples are made at a twist angle that's anywhere between 4 and 5 degrees. If you're interested in what happens at smaller twist angles, I can talk about it later, but let's ignore that for now. Okay, so let's start with the very basic picture. How do I understand the electronic structure, the band structure of twisted WSe2? So if I take one layer of WSe2, it is a triangular lattice in real space. So here's the reciprocal space version of this. It has, if you're close to the band edge, then its contours of constant energy look like circles, which are centered around the K point, similar to graphene. And if I have two of these layers and these two layers are misaligned with respect to each other by some angle, then I have two of these bands in reciprocal space, which are also rotated with respect to each other by the same angle. And so if I take a cut through, for example, this line, which goes between two of these circles, then I'll see something that looks like this. I see a conduction band and a conduction band from the two layers, which are offset from each other because of the twist angle. And one of these is around the K point, and one of these is around the K prime point. And also, I'll see a valence band for both of them. Now, of course, the way this is drawn makes it look like the gap is small. The gap in these systems is actually enormous. It's on the order of 1.5 or more eV. And so effectively, we work either in the valence band or in the conduction band. And for the case of WSe2, it's easiest to work in the valence band because that's where you can make nice devices. So all of the physics that I'm going to tell you about is essentially occurring in this top part of the valence band. And all you need to worry about is the very top of the valence band, which kind of looks like that. Okay, so when we made our first set of samples and we measured them, this was sort of the transport data that we measured. And what I'm showing you here is a longitudinal resistance of a sample as a function of doping. So doping here is on this axis. And 0 here is the valence band edge. Near the valence band edge, you see insulating behavior. This is just because it's a crappy semiconductor when you're close to the edge of the valence band. And as you start doping, you start seeing conduction. And if you take a sample that has two layers which are aligned with each other in natural alignment, this is a so-called Bernal stacking, the conductivity of the sample just keeps increasing as you pump more and more carriers into it, and it just becomes a good metal as you dope it more and more. On the other hand, if you choose a sample which has a twist in it, so this is 4 and various different angles, you notice something interesting. You notice that there's a peak in the resistance, and this peak turns out to be an insulating peak. If you measure the temperature dependence, this turns out to be an insulating state. And this insulating state, if you work out the numbers, you will find out that it occurs precisely at half filling of this lowest subband. Okay? And the reason that it occurs at different values of density is because as you change the twist angle, you change the size of the unit cell, and therefore the absolute density that you require to reach the half filling condition changes. Okay, now one very interesting thing that we found, which in retrospect is fairly obvious, is the effect of an electric field. So an electric field is if I apply a field that is perpendicular to these two layers, this can actually tune the bandwidth of this band. And the easy way to see this is the following. So let's go to that picture that I showed you earlier and zoom in just to the top of the valence band. So this is the valence band from one layer. This is the valence band from the other layer. And if I apply this electric field, then the two layers have different electrostatic potentials because I have integral E dot dl. And what this means is that the valence band from the top layer is going to go up and the valence band from the bottom layer is going to go down. And then if I work out what happens in a more systematic way, this is with DFT, you can see that when I start to apply electric fields, you see this effect. You see one of these bands go up and the other band go down. And this therefore tunes the bandwidth of the system. And also a very important detail that I'll come back to several times in this talk and you should pay attention to is if I look at this particular band structure, there's a particular point right there. This point is a saddle point in the band structure. It's a Van Hoff singularity. If I go in this direction, you see that it has a curvature up. If I go in the other direction, it will have a curvature down. And it's therefore a peak in the density of states. This peak in the density of states occurs somewhere between the top of the band and the bottom of the band. And as I apply this electric field, I can tune where this Van Hoff singularity lies by just changing the value of the electric field. And this is a very important thing. Okay, so what we did is we measured as a function of density. Density is on the x-axis, and the electric field is on the y-axis. And we measured around this half-filling point for a range of samples. And what we saw is that for a range of samples, you see insulating behavior. And this insulating behavior lives in a little pocket that is right around half-filling. Okay? And so that's sort of the picture of the band. I've half-filled this band, and when I have a half-filled band, I have an insulating state instead of a metallic state. So this was sort of the first finding. The way we rationalized where in this phase diagram of electric field and density the insulating state appears is by looking at the value of the density of states. And what we found is if you look at theory and ask yourself, where is the density of states maximum? In other words, where is that Van Hove singularity close to half filling as a function of twist angle and as a function of electric field, then we find that it is indeed maximized in this range of angles and at some range of electric fields. And that's indeed around the place where we see insulating behavior. So the picture that emerged from this first work is that we are in a regime of moderate correlations where the density of states helps us enter into some broken symmetry phase, and this broken symmetry phase has a gap in it. Okay, so now I'm going to go very quickly into the second part of the story, and I'm going to be very brief because this is theory. So this is theory from Andy Millis and his collaborators. And I should say that this is Hartree-Fock theory. And I should also say that there have been many, many works done which I'm not referencing here. And if you're one of the authors who've done one of those, I apologize in advance. What Andy said, and this basic point is something that I want to reiterate, is if you look generically, you will find that there are many different types of broken symmetry phases that are possible in this system. And in general, this is always true because there is a Van Hove singularity in the system. And whenever you're close to a Van Hove singularity, in Hartree-Fock theory, you will very often find these kinds of broken symmetry phases. I don't mean to convey a whole lot from this other than to say that all of these phases are magnetic in some type or the other. So there's various types of antiferromagnetic phases. Here's a stripe phase. Here's a 120-degree Néel phase. There's also ferromagnetic phases, and so on and so forth. And the general picture at this level of theory is that as you change doping and you approach this half-filling point, here is the half-filling point, you first have a transition into a metallic magnetic state with this kind of symmetry breaking. And then as you crank up the strength of that order parameter, you can eventually enter an insulator with magnetic order. And then as you go through half filling and go out the other side, you still have some metallic magnet until eventually you go over into a paramagnetic phase. Okay, so yeah, so I already said this. And the basic physics of this is basically the physics of a Stoner instability in a ferromagnet, right? So in a ferromagnet, you know that it's not just the strength of the interaction that matters, but it's the strength of the interaction times the density of states that matters. And something very similar would happen with all kinds of density wave orders. And so the basic idea is as you approach the Van Hove singularity, you have some strong nesting towards some type of order, and this gives you an ordered phase, some kind of density wave order. No, both values participate. In the order you yes, yeah. Okay, yes, please. So it's of order tens of millivolts, maybe up to 100 millivolts. Yeah, so the bandwidth is also in the order of 50 millivolts. So yes, if you're to do something serious, then you should take higher order subbands into account and longer range interactions also into account. Okay, so now in our experiment, at least in our first experiment, we could not see any evidence for this metallic magnetic state. What we saw was evidence for an insulating state, but of course we don't know whether it's magnetic or not. So we started looking more carefully at what happens as you go near the boundaries of this insulating phase. And one of the interesting things that we found that's in the second work is, I'm just drawing here in a cartoon form, this is where that insulating phase is located as a function of electric field and as a function of density. This is for two different angles. And you can go and look at the behavior of the sample by measuring its resistance as a function of temperature and figure out whether the sample is insulating or metallic. And you can also measure the size of the gap from an Arrhenius fit. And if you plot that as a function of electric field, that's the blue line, or as a function of density, that's this purple line, and you measure the gap as you cross this ring, what you notice is that the gap goes continuously to 0. Right? And this gives some what can I say, some support for the idea that you have a continuous phase transition as you go from here, from this insulating phase to this metallic phase. And it sort of fits in with the theory that there is some magnetic order that's on this side and on this side, and the gap eventually opens when that order is strong enough. But of course, again, here, we are not directly measuring magnetism in any way. And it turns out that if you measure transport signatures in the vicinity of this kind of critical point, you indeed measure lots of interesting and fun properties. For example, there's a region of T-linear behavior, and so on and so forth. All of that is interesting, but directly by measuring the transport in this kind of region, it's difficult to tell if I have a magnetic phase that's present or not. Okay? So, please. As against a Mott insulator. So, you know, I'm measuring transport, so I can tell you it's an insulator. Anything beyond that is theory. Okay, so with this now, let me go to the, yeah. Yeah, what is the best evidence for that is, so certainly we have samples which are more inhomogeneous, and there you kind of see insulating behavior at random points in the phase diagram. So this is always pinned to half filling. Is disorder important? I'm sure disorder is important, right? You know, the best we can say is experimentally we see it for a range of samples, range of dopings, et cetera, but we don't have a very good quantification of what the strength of disorder is at this point. And this is true in all experiments in this field. Okay, so the next part, which I'm going to spend a little bit more time on, is we wanted to track down this idea that there could be some magnetic order present in the system, even when it's a metal. And so I'll show you some transport evidence for this. So I'm showing you a sort of different sample, but very similar. This is 4.2 degrees. Once again, here I'm plotting the, this is the Hall resistance. Okay, the Hall resistance as a function of electric field and doping. And we have this bad habit of putting 1 here sometimes and half here sometimes. This is half filling. So depending on how you count, sometimes this is half and sometimes this is 1. But the insulating phase in this particular sample is located around here. And what I'm going to show you are data that's taken away from the insulating phase. So in particular, I'm going to show you data that's taken along a cut that goes in this particular direction. And nowhere along this cut is a sample an insulator. The sample is always a metal. And what I want to show you are transport data and convince you that this kind of interesting behavior that you see here is associated with a magnetic metal. Okay? And so here are a set of these data. And what these data are is as a function of magnetic field. The magnetic field is along the y-axis, and one of the gate voltages that I use to tune the density, that's along the x-axis, and the band edge is somewhere around here, and this is tuning the density. And half filling, now I've gone to the -1 notation, half filling is right there. If you look at half filling in this particular sample, there is no hint of an insulator whatsoever. But I hope all of you see that there's some interesting behavior that happens right around here, something that I want to talk about. And this is done for one value of electric field. This is done for a different value of electric field. And finally, if I tune the electric field just right till I reach that insulating phase, at this particular value of the electric field, I've hit that insulating phase. You can see that insulating phase, which appears precisely at half filling. But at these values of electric field, there is no insulating phase at half filling. And I want to talk to you about what the magnetotransport looks like at these values of electric field. Okay, so, and I'm going to concentrate primarily on the Hall effect. And so this is a longitudinal resistivity. If I plot for you the Hall effect looks complicated. So here you can see all kinds of different colors. And the colors here, red color here is a positive Hall coefficient, and blue color here is a negative Hall coefficient. Okay, so let me walk you through this a little bit and try to convince you that there's something interesting. Okay, so let's first take the theoretical band structure. So this is the theoretical single particle band structure, and ask ourselves, what should the Hall effect be if I just take non-interacting electrons, put them in a band that looks like this, and measure the Hall effect? What should the Hall effect be? Well, our textbook tells us that the Hall effect goes as 1 over the density. And here, when I'm close to the edge of the band, I have a hole pocket, and I have a hole pocket, hole pocket, hole pocket. The hole pocket is getting bigger and bigger, which means the Hall resistance is getting smaller and smaller in sort of a 1 over n fashion, until I hit this Van Hove singularity. And when I hit this Van Hove singularity, I should go from holes to electrons. And so I should have a sign change of the Hall effect. And then I have electrons, and then electrons, 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 all the way till I reach the end of the band, where once again, I have a large Hall coefficient. Okay, so this is the theoretical expectation for what one should have. Let's look at experiment and see what experiment says along this same region of density. So if I'm somewhere here, far away from this Van Hove singularity, I measure the Hall coefficient, and you look at low fields, ignore what happens at high fields. You see, indeed, it has a nice linear behavior. You can extract a density from this, and you can put it onto that, and it works out pretty well. Within a few percent, it's where it should be. Now, I come closer, you see that the slope of this thing changes, but the same thing. But now I come pretty close to the Van Hove singularity, and you see something quite different happens. So now if I look at the Hall effect indeed has that same slope at low field, but if I go over to higher field, you see that the sign of the Hall coefficient changes. And this is very common in a system that has multiple bands. You'll see this kind of behavior. And now if I go sufficiently far on the other side, this behavior starts to disappear, and eventually I get an electron band, as I should. So close to the Van Hove singularity, the Hall coefficient deviates from the single particle expectation. And if I plot the low field Hall coefficient as a function of density, you can see quite beautifully that if I'm far from the Van Hove singularity, so the Van Hove singularity here is at minus 1.1 roughly. If I'm far from this point, I have more or less the non-interacting expectation on the hole side and on the electron side. But if I'm close to the Van Hove singularity, I have this gigantic peak. And this is our primary evidence that you have a Fermi surface reconstruction in this particular system. And this is just sort of putting all of the data together. You can see the nice evolution from the hole side to the electron side, and in between this interesting behavior. You can try to track down and see whether there's evidence that this is a real phase transition. So what you can do is you can apply higher temperature. So this is higher temperature, and you can also look at as a function of magnetic field. As a function of temperature, this behavior disappears by around 30 Kelvin. And so our evidence that this is a real phase is from this sort of behavior. If you go to high enough temperature, all of this behavior disappears, and it more or less matches the non-interacting expectation. And if you apply a magnetic field, then with a reasonable magnetic field, again, you can quench this behavior, which is our evidence that this is somehow a magnetic phase. Okay? And let me just tell you what we think this is. We think this is 120-degree Néel order. This seems to be the most likely thing. When you're close to the Van Hove singularity, this kind of order sets in. And here's sort of some calculations from Andy and collaborators for what happens when you have this kind of magnetic order that sets in. I hope that's not me. Okay. So this is the band structure before the reconstruction. There's the Van Hove singularity. And if you put your chemical potential in the vicinity of this Van Hove singularity, then you have a Fermi surface reconstruction. When you have this Fermi surface reconstruction, you can see that there's both hole and electron pockets, and that changes the Hall coefficient, as one should expect. And we can sort of make a reasonable picture for how Fermi surfaces evolve and all this sort of stuff. I should stress that all of these things are just theory. We don't measure these things in theory, in experiment as of now. But our evidence for all of this is from the Hall effect. Okay, very good. So with this, I'm going to go to my final topic, which is superconductivity. And this actually is fairly recent work from this year. And Inji was making a sample which she wanted to make at 4 degrees to follow up on some of these measurements. Unfortunately, when she made the sample, it turned out to be 5 degrees instead of 4 degrees. This happens from time to time. But Inji, being a diligent student, stuck it and measured it. And she measured it for a while and found nothing interesting. And we were thinking of throwing the sample away. And she said, no, I'm going to measure it in the dilution fridge. And she stuck it in the dilution fridge, and hey presto, the sample became superconducting. Okay, so that's this story. Now, again, I'm going to start with the phase diagram. So this is density along this axis, and this is electric field along this axis. And I'm going to show you first the longitudinal resistance. So this is longitudinal resistance on this phase diagram, as well as the transverse or Hall resistance that's shown here. And there are many things going on here, which I'll clarify later, but I want to give you a few markers for what various things are. The first and perhaps most important thing you should notice is that if I sit at 0 electric field, and if I sit at half filling, so -1 is right there, and I measure the resistance as a function of filling, then you'll see that this particular sample has no insulating phase whatsoever. Right? In fact, it has no insulating phase anywhere until you get very close to the band edge and you have disorder. The second thing I hope you can see, all of you, is that this dashed line, which is drawn in a schematic here, you can see a faint thing in Rxx. And even better, if you look at Rxy, you need to think about this a little bit, but you can see a sign change of Rxy that happens right here. That's the white region. And that's once again the Van Hove singularity. Right? So here's the Van Hove singularity line. And if I sit at 0 electric field, the Van Hove singularity is here. And if I tune the electric field, as I told you earlier, I can tune where this Van Hove singularity lives in the band. And so this line has some curved shape that looks like this, goes like this. Okay. For those of you who have been following this work for a little while, I do want to say something. If you've not been following it, don't worry about what I say next. In our very first work in 2020, we had measured a sample that was very close to this 5.1 degrees. And in that sample, we did see an insulating phase. Right? And if you ask me what's different between this sample and that sample, one thing that's very different in this sample is that in this new sample, for whatever reason, I don't know what was going on in Inji's head, she made the dielectric thickness very thin. She made it 5 nanometers, which is much thinner than the dielectric thickness that was used in the previous sample. Okay? So in the previous sample, we had a thicker dielectric. We did see an insulating phase. If you read our paper carefully, we claim to see superconductivity near the edge of the insulating phase, but the referees made us retract that statement because we didn't have enough evidence at the time. So we stuck it in there and kind of buried it in the paper. But exactly at the same place in the phase diagram, we see superconductivity again now much more clearly. But the difference between the new sample and the old sample is that the new sample does not have this insulating phase anywhere. And it's possibly because the dielectric thickness is thinner, so screening is better. Okay, but let me now concentrate on this part of the phase diagram as a function of electric field and density. And in particular, this little dark blue thing here, that is superconductivity. Okay. So zooming in right there, this pocket here, this pocket is 0 resistance. And I hope all of you see that around this pocket, you have something interesting going on. And just to show you some line cuts, that if you're sitting here and you measure resistance as a function of temperature, you indeed see a superconducting transition. The maximum TC we see is around ½ a Kelvin, so it's not going to impress anybody as a superconductor, but still it is a superconductor. And if you go away from this point, then you see normal state if you go somewhere away. And I have to say that we have not characterized the normal state particularly well. So if you're interested in knowing whether the behavior is still linear and so on, we don't have great data on this just yet. Okay, so just to show you a few characteristics of superconductivity, you can see that there is a critical current. You also measured Fraunhofer patterns in this. You can measure the magnetic field dependence. So very modest magnetic field, few tens of millitesla suppresses this. So all good things for a superconductor. You can calculate a coherence length and a mean free path. And what you'll find is that this ratio, if you just do this from the magnetic field, is about 1/4. Okay, so now the most interesting thing, as far as I'm concerned, is to ask what is this thing that is immediately adjacent to the superconductor. And one way we can study these things, there are two ways we can do this. One is we can raise the temperature till we are in the normal state, or we can apply a small magnetic field till we are in the normal state, and then look at this particular region of phase space and ask what does the resistance look like. And here this is done at a small magnetic field. If you apply a small magnetic field, you see very clearly that there's this little region here that's interesting and looks different from the region around it, right? And this has precisely the same phenomenology that I was talking about earlier of having a Fermi surface reconstruction. So we believe that this particular thing that is adjacent to the superconducting phase is indeed an antiferromagnetic metal phase. And let me just show you some of the transport data in that region. If you measure the Hall effect, once again, you see this very nonlinear Hall effect, just like I showed you before. I'm not showing you data at densities that are far away. That looks exactly the same as the previous samples. If you look at the longitudinal magnetoresistance, this also shows these interesting signatures that go along with the same field scales. So everything here in this particular sample points to the fact that we have an antiferromagnetic state that's right there in the vicinity of the superconducting phase. So if you put all of this together, this is sort of the phase diagram that you get, that there is some antiferromagnetic metal. And I have to confess that transport is not the best way to tell you what really the boundaries of this antiferromagnetic metal are. And so I cannot tell you if it ends abruptly here or if it goes a little further there. That's difficult to tell. But what we can clearly see is that there's some boundary between this phase and the superconducting phase, which is very sharp. We can watch the evolution of that boundary as a function of temperature. So here are data taken at a set of different temperatures from 30 millikelvin to above TC, the highest TC. And what you see is you see this arrowhead-like shape. And the shape of this arrowhead, the size of this arrowhead keeps shrinking as I increase the temperature. But I hope all of you see that this particular boundary here, this boundary here, remains reasonably sharp all the way up to 400 millikelvin. But the other boundary that's down here, it disappears in a continuous fashion. And so if you ask me what's going on with superconductivity, if I was to measure TC at different points, I would tell you that TC continuously drops to 0 as I go down this particular way. But TC, there's some sharp jump of TC as I go from here to the other side. Yeah, so straight boundaries of the antiferromagnet and curved boundaries of the metal. And this is sort of a contour plot of where superconductivity lives at different temperatures, telling you essentially the same thing. If you go across this boundary, so if you're very close to this boundary between the superconductor and the antiferromagnet, what you very often see is you see the remnant of a transition, but then it goes to a non-zero resistance at low temperature. And this could be a signature of perhaps phase coexistence. That's possible. Could be other reasons too. But you see that there's still a fairly sharp superconducting transition and then non-zero resistance if you're very close to this boundary. We can do a little bit more. So what I can do is I can go along this particular line and I can plot the resistance as a function of density, and I can sweep back and forth to look for any signs of hysteresis. And we see small signs of hysteresis. So it depends on how kind you want to be to us. But certainly this is reproducible. You see some hysteresis a little bit on this particular boundary, whereas at this particular boundary, we cannot see anything at all. And this kind of hysteresis has been seen both in bilayer graphene by Andrea Young and by Mandar Deshmukh's group in twisted trilayer graphene. Okay, so what's a plausible scenario? So what we know for sure is both this magnetism or this Fermi surface reconstruction and superconductivity lie near the Van Hove singularity where the density of states is high. That's, that's kind of obvious in all situations. And now one can ask, if this superconductivity is phonon driven, then why does the superconductivity have to lie there? Why could it not lie there? There's a Van Hove singularity here and a Van Hove singularity everywhere along this line. Why does it decide to live near the magnetic state? Could be it's a pure accident. This is a place where the density of states is maximized, and it's good for superconductivity in whatever mechanism. But there's sort of a more natural and tantalizing explanation is that this superconductivity is somehow related to the destabilization of magnetic order. So it's mediated by magnetic fluctuations. But this is a speculation at this point. What we know for an experimental fact is that these two phases basically live right next to each other and only in that region. Okay, so that's all basically I had to say. I think I'm good on time. And I'm just going to put up all of the things that I wanted to say right there and conclude. And thank you.
Time for questions.
Hi, Abhay. So what's the evidence that it's an antiferromagnetic versus any other magnetic ordered metal? Do you see it in transport?
Yeah, so certainly it's not a ferromagnet. So we see no hysteresis. And there have been some optical measurements which would have seen ferromagnetism if there was ferromagnetism. At lower twist angles, you do see ferromagnetism appear. So ferromagnet phases are not far away from this. And Xiaodong has some data on ferromagnetism at lower twist angles. But at these twist angles, there's no evidence of ferromagnetism from optics. And there's no hysteresis seen in transport. Now, ferromagnetism by itself, it would do something different to the Hall effect. But this sort of simple picture of the Fermi surface reconstruction would not be the same in a ferromagnet. So it's all circumstantial from the perspective of transport. The only concrete thing is you don't see any hysteresis in transport.
Can it be a fluctuating moment phase like Andrea, like in magic angle graphene and now in Bernal bilayer graphene is seen?
Yeah, I don't know enough about that. So the question would be whether that kind of fluctuating phase is sufficient to have a strong signature in the Hall effect. I don't know.
Thank you. Can you rule out coexistence of antiferromagnetism and superconductivity? You sort of implied that there was some first order like transition and there wasn't coexistence.
Yeah, we cannot. So all we have are transport data. It's entirely possible that even when you're well within the superconducting phase, that the sample has antiferromagnetism at a higher temperature and then is superconducting at lower temperature. That's entirely possible. We don't have any evidence one way or the other.
So you're saying at the moment there's no real method to measure in the superconducting phase to see if it's still antiferromagnetic?
That's right. So we can measure just from transport the regular signatures of superconductivity in transport, but to tell that it's also an antiferromagnet, that requires a little bit more work, I think.
Yeah. I was interested to know if you measured the volume fraction, the superconducting volume fraction, say through Meissner-like response or something, a diamagnetic screening response.
So far, none of those things are directly possible. These are all just transport, so we can tell basically resistive signatures. So it's feasible to do this with NVs, for example. But it's not an easy experiment. The volume is nothing.
Okay.
Yeah.
And I also wanted to know that in this superconducting phase, if you apply a strong magnetic field and you suppress the superconducting state, do you see any antiferromagnetic fluctuations persisting in the normal state in that region, or?
Yeah, so that was one of the slides I flashed, that if you go to 100 millitesla where superconductivity is suppressed, and you look at the phenomenology, you see evidence in the Hall effect for this Fermi surface reconstruction. Okay. And so, yes, indeed, we do think so.
I see. Thank you.
Okay, so
there's a question back there. Arun, there's one back there.
Yeah, so I have a question related to the first question. So you see there is a change in the slope of Hall, and you tell it because of its multiband. But does that tell that really antiferromagnetism is there from Hall data?
No, all it tells you is that if you take the data literally, that it's a multiband, that there is a Fermi surface reconstruction, right? If you ask yourself what is the real evidence that it's a spin density wave versus a charge density wave, for example, it would just be the sign of the interaction, which we have no reason to believe it's attractive. And so that's really a theoretical statement. But any Fermi surface reconstruction would reconstruct the Hall effect.
Okay, thank you.
So I just wanted to ask, like, how robust is the dependence of the superconducting phenomena on the angle? Like, is it like limited to 4 to 5 degrees only, or like is something like a magic angle present here as well?
Yeah, so what we have is we've measured superconductivity in a sample that's 5 degrees. We've done it a couple of times now. The reality is that in our older work, this happened at a time when none of us at Columbia had a dilution fridge, believe it or not. And Corey got a dilution fridge like a couple of years ago. And this is, so all the older samples might have all been superconducting. We just never measured it below 1 Kelvin.
Regarding what you showed in terms of the screening behavior, you explained that because the thickness of the HBN is thinner, maybe you screen better and you don't get an insulating state. But a thickness of 5 nanometers means that you screen really long-range interaction. But the belief is that the insulating state are driven by local on-site interaction. So maybe can you comment on that?
That's not clear to me in the TMDs. I think in the TMDs, at least from Andy and co-workers, the interaction is fairly long range.
But this is what determines the insulating state, long range?
Well, take for example this Wigner crystal, right?
Yeah.
The Wigner crystal is formed at sort of 1/3 density. So unless the Coulomb interaction cares about what happens 3 sites away or 2 sites away.
But the 1/3 is much weaker than the 1, right? So,
Yeah.
so obviously there are longer range interactions, but are they essential for the nu equal 1?
Yeah, that's a good question. My guess is that if you take these kinds of magnetic states, that they would indeed be important, the longer range interactions, but I'm not a theorist, so I don't know the exact details of that. There's some work by a different set of Andy's collaborators on this.
One final question from Oscar, and then we should move.
How sensitive is your insulator at nu equal to -1 to the external magnetic field, particularly if it's perpendicular?
Yeah, so that's an interesting question. So it's fairly sensitive. So by about 3 or 4 Tesla, you generally lose this insulating phase. Something interesting happens at very high field. If you go to above 20 Tesla, you have a reentrant insulator, which we believe is actually an excitonic insulator. So the Zeeman effect in these things is very strong. And so if you get to about 20 Tesla, you have an enormous Zeeman effect to the point where you almost spin polarize the carriers, but not quite. And then you can get an excitonic insulator.
Thanks.
All right, with that, let's thank Abhay for this very nice talk. Our next speaker is Manish Jain from the Indian Institute of Science. All right, so this next session, next talk will be by Manish Jain, and he'll be telling us about phonons in these twisted Middey.
All right, first of all, I'd like to thank the organizers for giving me this opportunity, and I apologize to every one of you because one of the things I didn't do, or I thought I did, is send them my title, the title of the talk. So apparently it's not on the website, and that's probably just me not sending this thing in at all, or thinking that I've already done it. In any case, I'm going to be talking about phonons in Middey materials. So here's a brief outline of the things I'm going to be talking about. We've heard a lot of things about electronic structure in these twisted TMDs, for example, in Abhay's talk just before this one. But there's also some very interesting things that one can do with phonons in these materials, and that's one of the things that I'd like to focus on. So I'll talk about low frequency phonons in TMD bilayers, the Raman active modes in twisted WSe2, the same material that Abhay was talking about, and Raman line width in the G mode in twisted bilayer graphene. So, okay. So, as we have all seen, twist is a very interesting degree of freedom, and most of the time people are interested in the flat bands that originate from twist and all the associated electronic properties that come with that. But there is also some very interesting things that happen when you twist two materials. For example, you see these super lubricity. This is seen in graphene. When you take one piece of graphene and rotate one layer of graphene and rotate it with respect to the other one, at some point the coefficient of friction becomes nearly zero. And of course, there are all these by now very well known domain wall networks and topological point defects in these systems. And so the question that we are sort of asking is, this is structural. This must have some origin in some phononic kind of properties as well. Is how does twisting actually affect the phonons in these materials? Since Abhay has already given an introduction to TMDC bilayers, let me just briefly say what are the kinds of structures that you form when you twist one layer with respect to another. If you take a TMD bilayer and you rotate with an angle close to 0 degrees, then you get one kind of stackings, which is the AB and the BA, which are essentially the same stacking, and these are called the 3R stacking, if you wish. And then there is this AA stacking, which is nominally unstable. On the other hand, if you go near 60 degrees, you actually see a different kinds of stacking, which is the AB prime and the A prime B, and the 2H stacking, which is the natural bilayer of TMDCs. Okay. Now, if you just construct these structures and you start asking the question, okay, if I let it relax, then what really happens in the system? What really happens is the following. I'm showing you, sort of a calculation of the interlayer separation landscape. So we're just looking at the interlayer separation, and we are just going as a function of angle. As the angle becomes smaller, and as you're going closer and closer to 0 degrees, what you notice is that, we know that the Moiré length increases. But what is also quite striking is the fact that it increases only because some regions of the high symmetry, some high symmetry stacking regions actually increase in area. The unstable stackings, which is this AA stacking, it actually doesn't increase in area as uniformly as the separation increases, right? So essentially what you get is these domain wall networks, which are very well known, and as the angle decreases, all that happens is the area of this stable stacking keeps increasing. Now this is near 0 degrees in TMDCs. If you go near 60 degrees, you basically get a slightly different looking picture. It's more or less the same, except one thing that is different about near 60 degrees is that these two stackings are not the same. I don't know if you can see it very clearly. There are two dark blue triangles here, if you can see. So these two dark blue triangles are not exactly the same area. One of them is larger than the other, and as a result, these domain walls sort of are curved with respect to, they're no longer straight. And this can have some interesting consequences on if you make these domain walls curved enough, at some point you would think that because these cost energy, that the system might reconstruct, and that doesn't seem to happen in many systems over here, but I think if you tune strain and stuff, you can probably make a moire reconstruction happen in these systems. Okay, now the interesting thing to note here is that some of these stackings are actually unstable. Okay, so if you were to try to make this experimentally, you would not be able to make it. It would not stay there. Whereas the AB and the BA are actually stable stackings. And similarly here, the AB prime and the AA prime are the stable stackings, but the A prime B, which is these red triangles, these are actually unstable stackings. Yeah? Okay. So now the thing that we would like to do with the structural stuff out of the way, the question that we would like to ask is, how do I go about calculating phonons for the system? I'm a theorist, so I do calculations. So the question that we are asking is, how do you go about calculating phonons in the system? Now, you can of course construct a geometrically commensurate superlattice. Real lattices may or may not be commensurate, of course, but you can find something which is close enough and say, okay, that's probably going to have similar properties. The problem is, these systems, if you construct them, the superlattice will have tens of thousands of atoms in them, right? So there is no possibility of doing a first principles phonon calculation on the system at all, right? So the next best thing, there are many possibilities. One is you could write a continuum theory for this. That's one way to go about doing this. The other possibility is you can actually go to these interatomic force fields, right? Interatomic force fields there's an atomistic description, but there are no electrons. The electrons have all been integrated out. We only have forces on the atoms, and that's essentially all we're going to work with. Now, one thing that you have to make sure that this force field does correctly is because in a given stack, in a given structure, you have multiple stackings present simultaneously, right? So you want to make sure that the force field that you use actually describes all the stackings correctly. And for that, people have come up with these. Kolmogorov and Crispy had given a prescription of how to construct such a force field. And there are many others. There's something called drift, there's interlayer potential, and many others, right? And one thing that you have to make sure is that you use any one of these methods, because then you're guaranteed that all stackings are described properly in your system. Then, of course, is the problem of, fine, you have the force field. So in principle, you can construct dynamical matrices. But you still have to construct them and you have to diagonalize them with these force field that you have. And for that, we've actually written a code called PARFORM. It stands for Parallel Phonon Calculator for Moire Systems, which is going to be available soon. Essentially, what it does is it takes these force fields, which are fed into a software like LAMPS, which is very often people who do these kinds of calculations they use. It will then calculate the dynamical matrix, the force constant matrix from there, and Fourier transform it for you. These matrices can be large. If you have 10,000 atoms, then your matrix will be 30,000 by 30,000. So you need a way of diagonalizing it and so on and so forth, which is all done in this package. Okay. So let's say you did all of this, and then you did the calculation. This is what you'd get, right? I don't know about you, but this is spaghetti. Right? That's all. I don't know how to make sense of this, right? There's a lot of phonon bands that you get, and you have to now start to ask the question: how do I make sense of this? Right? This is too many phonon. This is done for 2-degree twisted bilayer WSe2, right? So the thing is, in principle, once you go from here, you know this is good. You knew this was going to happen, because if you have n atoms in the unit cell, or in this case the Moire cell, then you have 3n bands at every phonon bands at every k point. Now, what you cannot do is you cannot try to analyze them in the standard way in which you analyze, let's say, your phonon bands in a unit cell with let's say, 3, 4, 5, or 10 atoms in it, right? One thing that you immediately realize is the Moire lattice doesn't have the underlying symmetry, may not have the underlying symmetry of the unit cell lattice, in which case you have to characterize this. Even if you wanted to do it with group theory, you would have to characterize it with a different group, which is fine. But even so, there'll be too many bands. And I'm not sure what you'd gain by doing that, right? Let's say you even did that, it would still be a large number of bands. The thing to realize is that the Moire lattice is by and large constructed of a folded version of some kind of a, each layer of course is a folded version of its, because it's a supercell that you've constructed. So one way in which you can identify the Moire modes is by recognizing that these are folded versions of, let's say if you're interested in Raman active modes, these are folded versions of the Raman active modes of a bilayer. That's one way in which you can sort of try to analyze all of this. Of course, these are not just the simple bilayer modes of the individual layers. The two layers are talking to each other. That's the whole reason why this is all very interesting, right? So a simple way in which you can try to understand what is, let's say if you're interested in comparing this with Raman spectra, is by projecting these modes onto a bilayer-like mode, and I'll describe what this means in a minute, by projecting the Moiré modes that you get onto such modes and then try to see if you can make some sense of that. Okay, so this is sort of the general program that we're going to follow. You could come back and you could say, look, in principle, what one could do is actually calculate the full Raman tensor, right? You could actually calculate the Raman tensor and the Raman tensor will tell me what is Raman active. I don't have to decide a priori how to do any of that. Problem is it's a third derivative of the susceptibility. It's pretty hard to calculate. So this is sort of a poor man's alternative, which is you say, I know that the bilayer mode was Raman active. So if I project onto that Raman active mode, maybe I get something which the experiment sees. Okay, so with this program, let's start thinking about low frequency phonons in TMDC bilayers. Okay. So as you are all probably very familiar with this, a monolayer, of course, has, if you look at just the low frequency part of the spectrum, this is frequency versus wave vector. You have three modes here, the out of plane vibrations and two in plane vibrations, vibrational modes, the longitudinal acoustic and the transverse acoustic modes. Now what happens is when you put two layers together, you still will have only three modes at q equal to 0, but the second layer also had these acoustic modes and they sort of hybridize and you start getting these the layer breathing and the shear modes. Essentially you have 6 modes now. 3 of them are gapped out, right? 2 of these are shear modes, which refer to these sliding of the 2 layers with respect to one another, and one is a layer breathing mode. Okay, and if you look at the eigenvectors corresponding to such modes, essentially these are just relative displacements of the 2 layers with respect to one another. Okay. Now, if you want to do this for let's say this is done for MOSE2 as a function of angle, you start seeing something quite interesting. So this is a busy slide. Let me take you through this. Essentially, what we've done is we've calculated the full phonon spectrum. And the phonon spectrum, as you might expect, is a mess. So to analyze it, we have projected all the modes onto these modes that I just showed you before, onto these shear and breathing modes. And I'm just asking, what does that projection weight look like, right? So I've calculated this projection weight, and I've plotted this projection weight as a function of angle and as a function of frequency. Right? So what you notice here is you notice something very strange. First of all, you notice that this is shear and layer breathing modes, right? You notice that there is a mode which is at very low frequencies. Right? Typically, when we do solid state physics, we tell our students there is the acoustic modes, and the acoustic modes are the only ones which are actually 0 frequency. But now I'm seeing some other mode which is shear-like, because the stars here refer to the shear-like mode. That is also very low frequency. Okay, so I call this ultra soft, right? Its frequency is less than 1 centimeter inverse. So 1 centimeter. So in region 1, you see these shear modes with frequency less than 1 centimeter inverse, and you see sort of an average layer breathing mode. Okay. Then when you go to region 2, you see an ultra soft shear mode. You also still see this mode, but now you start seeing that there are multiple of these layer breathing modes. So the circles here refer to the projections onto the layer breathing modes, which is basically I'm doing projections onto this. So I see multiple of these, but there's one shear mode, and then all of a sudden, as the angle becomes smaller, I start seeing these other shear modes appear as well. Yeah. So the thing is, okay, so you see what you see, but is this related to reality? It is. I mean, this we are comparing it to experiments. The green stars and dots are experiments, and the circles are the I don't know, brown or orange circles are calculations. and they're roughly in the same ballpark. So, the frequency, the numbers are not exactly precisely the same, but these are they're really close. So qualitatively, we are getting the right physics. So the question now you can ask is, the strangest part about all of this is, what are these low frequency modes? What do they correspond to? So when you look at this low frequency mode at a large angle, you start seeing, and I don't think you can see the arrows, but all the arrows are pointing in the same direction. So if you look at an angle, so let's say about 23.5 degrees, and I look at this low frequency shear mode, right? It is this mode, right? It's zero frequency. It doesn't cost any energy. And at larger angles, you start that this mode is actually starting to localize. And actually, if you notice carefully, these modes are actually localizing at all your domain boundaries. So first of all, you ask yourself, why are these modes zero frequency? I mean, when I look at a bilayer, these shear modes actually cost energy, as they should. Why is this not costing any energy? The simple way to understand this is to just to realize the fact that in a Moiré cell, I already have all kinds of stackings present, right? So when I shift one layer with respect to, when I shear one layer with respect to the other, I still have exactly the same stackings, more or less, right? Which means, in some sense, the cost of doing this is almost zero. Energy cost of doing this is actually zero. And this is actually this is actually well known. This is what is called a phase-on. This is called a phase-on mode. And this is essentially what is responsible for us seeing these nearly zero energy modes in these systems. Okay? But what about at higher angles? You again see these modes which are zero energy, and you start seeing that, look, they're localized on these domain boundaries. And let me see if I can show you what the motion of one of these modes might look like. So this is just the eigenvector of one of the modes, which is zero frequency. And I don't know if you can see, but if you notice here, this seems to be shifting, right? So this is sort of an effective Moiré lattice, the acoustic mode of the effective Moiré lattice, which is showing up. This is basically nothing but a phase-on mode. This is a phase-on mode which is associated with the Moiré lattice, which is showing up in this. I hope everybody can see that it's the whole the center of that thing is moving left and right. Right? Okay. So these are two sort of new and interesting modes which have shown up, which are almost zero energy. And then you ask yourself, well, how many such modes are there? And it turns out, when you look at, and this is not related to your twist angle, in the sense that even near 60 degrees, you see exactly the same things in MOSE2. And I believe it will be true for graphene and any other material as well. This has nothing to do with the TMDCs that we actually studied. In fact, in all of these modes, you start seeing that these are not exactly zero, right? But these are they're slightly gapped out right at the end. I mean, this scale is 0.4 centimeter inverse. This inset is plotted with 0.4 centimeter inverse, right? In some cases, they are below. That's a numerical artifact. We believe that it is slightly negative. I mean, it's minus 0.02 centimeter inverse. It's probably just a numerical artifact of our calculation. But by and large, you're seeing all the acoustic modes, and then you see suddenly these modes, and you see them, they turn around right at the end. So they are gapped out, but they're gapped out at 0.2 centimeter inverse of that order, which essentially is zero for all practical purposes. Yeah. They are Goldstone modes. There are indeed Goldstone modes. And I'll explain in just a minute. So these are ultrasound modes, which are optical modes. So at least in how we see it, and this is related to the fact that we've only done commensurate structures. So the physics of this actually is related to the fact that if you go to, let's say, the Frenkel-Kontrova kind of a model, which is just a simple model of, let's say, if I have a potential with a length scale B, and if I have, let's say, beads and springs with a length scale A between them, and if I make A and B incommensurate, then it is well known in the system, as long as A and B form an truly incommensurate structure, then a gapless phase-on mode will show up at omega equal to 0, which is basically a Goldstone mode. But if I make this thing commensurate, which is what we've done in all our calculations, right? So then this mode actually gets gapped out, but the gap is extremely small. So unless we are measuring things at very, very low temperatures and you can actually see that difference, it's probably not going to matter for most practical purposes. Yeah. Okay. I mean, that's sort of related to the fact that, if you don't have all stackings to begin with. In an incommensurate structure, you really had all stackings, right? This is a finite system, so which is periodically replicated. Okay. So that's all good and well. So what? So, one of the things that you find very, very interestingly in these systems is that you see that there is, if you plot frictional force as a function of misfit angle, and I think this is done for graphene or graphite-like structures, you see that the friction is only present when the angle is really small. Of course, they have a resolution of only 5 degrees, which is pretty good for experimentally. I can imagine doing this experimentally is much harder than doing it on a computer. Nevertheless, you see that it increases, but otherwise the frictional force is extremely small. So we think that this is related simply to the fact that the moment these shear modes, once they start splitting from this phase-on mode and they become more like your when they gap out by substantially when they go to actually the full shear mode frequency, that's essentially where you will start seeing this transition from a super lubric behavior to a sort of a pinning behavior. A simple way to understand this is to understand this in the following way. Imagine if all your stackings are roughly the same size, and there is no development of these large regions of AB and BA stacking. Then, in some sense, shifting this one layer with respect to the other will not cost you much energy. But on the other hand, the moment these regions develop and become large enough in area, then all of a sudden, when you shift in this area, there's a cost to actually shifting one layer with respect to the other, and so you should actually have some pinning kind of behavior that should happen. And this happens roughly at the angles when this happens when the shear modes actually split off and become from the zero energy phase on mode, they actually become finite in frequency. You can also look at this in terms of a potential barrier. If you take such a system and you sort of slide one layer with respect to the other, as the angle becomes smaller, the barrier to doing this becomes smaller, and you can also understand it in that way. Okay. So now let me quickly move to the second thing that I wanted to discuss, which is Raman active G modes in twisted WSe2. So, this is driven mostly by our experimental colleagues who from Anindya and Ajay Sood's lab. They measured a large number of twist angles near 0 degrees, and they saw that if you look at the G mode Raman frequency, that it seems to split, right, as a function of angle, and then the split sort of goes away. It becomes less as a function of angle. So what we wanted to do was try to understand how do we make sense of this data as to where is this split coming from. So this is their data plotted in the way that at least I look at it, which is that there's a Raman shift. There are 2 peaks which they have fitted to their Raman. This is the EG peak. They have fitted 2 peaks to it. And if you look at the position of the 2 peaks and you look at the difference between them, the difference seems to have this kind of a behavior. So, we're going to follow the same program that I told you about. And in this program, essentially what we're going to do is we're going to calculate the phonons, but there are too many. So we're going to project them onto the G modes. So, but I don't know how to define a G mode I know how to define it for a unit cell. I don't know how to define it for a twisted bilayer system. So I'm going to make it up, right? Hopefully you'll agree with what I made up. So I know what a G mode for a bilayer looks like. It looks like this, right? All the chalcogens moving in one direction and the opposite direction in the other layer, and the let's say in this case tungsten atom moving in opposite directions as well. So for the twisted bilayer, essentially all I'm going to do is put this displacement on one layer, put this displacement on the other layer, and then just put them together. Okay, that's what I'm going to define as the G. Now I'm going to call it the EG-like mode, right? Because it's not clearly not EG, because this would have been EG only in the case of a unit cell with 6 atoms. But nonetheless, it seems like a reasonable thing to do, at least to us. But now the thing that we are after is the splitting. So how are we going to get at the splitting? So if you look at, let's say, this the interlayer separation landscape, you notice that there are many different kinds of regions, which I discussed before. So what we're going to do is we're going to take the phonon eigenvectors that we get from our calculation at the gamma point, and we're going to project it onto different layers, right? And then try to see if the eigenvectors have different, have more weights in different regions, and maybe that's the reason why the split. So the idea is maybe the AB and BA regions have a different phonon frequency than, let's say, the AA regions. And essentially, when you measure both of these simultaneously, and that's the reason why you're seeing this difference. Okay. So when you do the projections, and there are many phonon modes. So I've done the projection for all the phonon modes. This is as a function of angle. You see that indeed we are sort of seeing an increase, as a function of angle. As the angle becomes less, the separation seems to increase, and then it seems to decrease. Okay. But now, if the idea that we had is correct, that if these are coming from different regions in space, then we should indeed see that this total thing that we are seeing over the entire sample is actually really coming from different regions, and there are different distributions in different regions. So for example, in this SP region, which is nothing but your domain wall kind of region, you do see that there is a different distribution than, let's say, in the AB and BA regions as they develop, and in the AA region. So we think that the reason why this is splitting is indeed because of this very simple reason, that as your angle becomes smaller, that these regions become larger, the AB and BA regions become larger and dominate your Raman spectra. Whereas when the angle was larger, these regions are all almost equal in area, and as a result you measure an average quantity, and that is sort of the reason why this thing goes up and then starts going down. The splitting goes up and then starts going down, because eventually if the angle becomes really small, right, the Raman signal will be dominated only by the AB and the BA regions, because those are the only ones that are growing, whereas everything else is not growing in area, and so as a fraction it is becoming less and less. So that we think is the reason, and indeed if you forget all of that and you say, okay, look, let's just calculate the difference, you've done this, you find that indeed it follows a similar trend. Yeah.
Basically what you're saying is that via the optical phonon you're measuring the gapping up of the
This is the EG mode. This is the EG mode. This is not the, this is 200, this is 200 centimeter inverse. Yeah.
measuring the interaction of the EG mode between the two layers, which is the same mechanism as the phasor mode.
That is sort of correct. That is sort of correct. But the EG mode is high frequency, but you're absolutely right. The two layers, the chalcogens are indeed moving opposite. Of course, the tungsten is moving in the opposite direction, but maybe that doesn't matter. Yeah, in that sense, you're absolutely right. Yeah. That's actually an interesting, I hadn't thought of that. That's an interesting way of looking at it. I hadn't thought of it in that way. But that's an interesting way of looking at it. So yeah, so this might essentially refer to the sort of the splitting of the phasor mode in some sense. Yeah. Okay. So now in the last 10 minutes, let me quickly talk about the Raman line width of the G mode in twisted bilayer graphene. So in twisted bilayer graphene near magic angles, there have been many interesting experiments electronically, but there's also some very interesting Raman experiments where they show that the Raman line width is much higher compared to what it would be for, let's say, an AB stack graphene. And in general, in twisted bilayer graphene, it is believed that the electron-electron interactions are perhaps the most important effect. But people do worry about electron-phonon interactions in these systems as well. And so what we wanted to do was sort of get a sense of how important are these electron-phonon interactions. And one way in which you can think about this is, if the Raman line width is increasing, I mean, it is coming from the electron-phonon interactions, and that sort of gives you some idea of how important such things might be. So what we thought about is if we could calculate the electron phonon, the Raman line width in twisted bilayer graphene, and line width in general, if you follow simple Matheson's rule, you should have a line width that comes from electron phonon coupling. There should be some line width that comes from phonon phonon coupling and from disorder, right? This is the hardest one to estimate, so we are not going to do it. We're just going to do both electron phonon and phonon phonon estimates of the Raman line. So now, unlike the phonon program that we followed, which we still will follow, we have to do something about the electron phonon coupling. We have to calculate the electron phonon coupling. So to do this, what we're going to do is we're going to calculate the electronic band structure using an atomistic tight binding model, right? With distance dependent Slater-Coster parameters. So our Slater-Coster parameters are now going to be distance dependent, and you'll see in a minute why we're going to do that. To account for some electron-electron interaction, we are going to include them only up to the Hartree level, not the Hartree-Fock level or anything beyond that, just the Hartree level. And we are going to follow the same program that we did for phonons. Now, the reason why we made our electron phonon coupling, our tight binding parameters distance dependent, is because then we can take the derivatives. Right? And once we can take the derivatives, you can actually just define your electron phonon coupling matrix element in this way, where essentially all the ingredients that go in here are either the phonon eigenvectors or the electronic eigenvectors or the distance dependent transfer integrals for whom we need to take the derivatives. So once we've done that, we actually get the electron phonon coupling matrix elements. This is easier said than done. These are very large number of elements. This is a large number of phonons and so on. So we make several approximations, but it's something that can be done. It was actually already done a while ago in this paper by Hyungjung Choi's group in 2018, where they tried to estimate the TC that might come from the electron phonon interactions in twisted bilayer graphene. Once we have that, we are going to calculate the line width by just using this very standard Midgall the line width formula under the Midgall approximation, and all the objects that we need for this entire calculation just come from the electronic band structure or from the phononic band structure. So with this, we are set, and we can actually calculate the line widths, and we can see whether it makes any sense. So again, we still need to define the Q like the G mode, which we define in exactly the same way as we did for the WSe2, namely that we just take the eigenmodes for the unit cell and we just impose it on both the layers. Now, one of the things that we would like to compute here is we want to compute the line widths, not just the position of the line. So we sort of have to define a spectral function, which is defined in the following way. If I didn't do any projection, I would just take every phonon mode, and if I have the line width for corresponding to that phonon mode, I would just construct a Lorentzian for that particular mode. But now, because we are looking at the projected mode, we actually have to do some projections onto this. It's just a simple technical thing, but it's important because once you do that, essentially, if you look at just the projections, you see exactly what I had shown you before. You see that the projection weights are sort of increasing as the angle decreases. Not the projection weights. The projection weights are what they are, but the spread is increasing as the angle decreases. But something interesting happens when you construct the spectral function. You start seeing that there is an overall two-peaked structure in the spectral function, right? This was kind of unexpected. We thought, we'll see one big peak, which is sort of what had been implied by previous experiments. So we were a little bit surprised by seeing that there are actually two peaks in when you fit the spectral function, and you can of course fit them and get your line width, overall line width from here. When you look at the overall line widths, they are of the order of, they go from anywhere from 16, 17 to about 10 centimeter inverse. And this is for various dopings and, for different angles, near magic angle. One of the line widths for the EG plus mode, which is the higher mode, the line width is higher than for the EG minus mode. There are some peaks here and there, and then you start worrying about, is this numerical artifact? Is this real? And once you start if you look at this peak in careful detail, you realize that this really comes from, the joint density of states is actually increased at this doping, and which is the reason why you actually see this peak. So you can actually explain all of this just in terms of simple joint density of states kind of an argument. Okay? So, but now the question is, where is the split coming from? And if it works once, you try it again, which is the following. We again try to decompose the phonon eigenmodes into different regions and see whether this is something that makes sense. This time we are doing a little bit the decomposition not just in terms of SP regions, which were the sort of the domain walls. We sort of define the domain walls also as between AA and AB and AB and AB differently. We call it SP1 and SP2 and see whether it makes any difference or not. And indeed, you again see that the phonon modes are actually localized very differently in all of these regions. And indeed, you see that some of these modes, are pretty strong in the AB region, whereas other modes are equally strong, are stronger in the SP1 region, right, or in some other regions. So again, the argument still carries through. At least that's what we think. But the other thing is that the real line widths were much larger. So you have to now. This was just the electron phonon part. What about the phonon part? So for that, we actually what we did is. We actually computed the anharmonic contribution as well, and because we are doing force fields, we can actually compute the velocity autocorrelation. The velocity autocorrelation, but here we will have to do it a mode projected velocity autocorrelation, where the mode is defined exactly in the same way. Once you do this, you start seeing that there's an anharmonic contribution as well, which also shows the two-peak structure, which you can fit again to you can fit and you actually get a line width out of all of this. So when you put it all, here on the other hand, if you look, as a function of temperature, this is just the phonon part. There's no electrons as far as this is concerned, right? You see a systematic reduction in the Raman frequency as a function of temperature. So the position is shifting to the left, but also So should I share my screen again? Okay. So as I was saying, the frequency changes as a function of temperature. The position of the peak changes as a function of temperature, but the line widths are more or less the same. They don't really seem to change too much with temperature. Now this doesn't work. I'll just skip through it. That's okay. I'll just skip through it. So then we started wondering. You do theory, you get something, and then you wonder whether this is actually true. So we actually went to our experimentalist colleagues Anindya and Darshit, and they actually measured the Raman spectra near magic angles, and indeed they saw clear splits, which we think are attributed to the reasons that I just discussed. So to conclude, essentially what I've shown you is phonons in Moiré systems can get significantly modified and hybridized because of interlayer interactions. I showed you low frequency phonons, and there are some interesting new effects like phasons which show up in these systems. And both the high frequency Raman modes in twisted WSe2 and the Raman active G modes in twisted bilayer graphene, not only show an increased line width, I mean in the graphene at least that's what we calculated, but also they split because of the fact that the modes coming from different regions actually have different energies. And with that, let me just thank the people who actually did the work. Most of the work that I talked about was done by Indrajit Mehti, who's now at, actually, I don't know where he's now at. Has he moved to Germany? Okay, so he's working with Engel Rubio now, and by Shinjan, who's now graduating and going to move on soon, and with Prabal and Professor H.R. Krishnamurthy, and these are the computational resources. Thank you all for your attention.
Time for questions.
Thank you very much. I had a question or maybe a comment about the incommensurate phase-on mode, because there's a little bit of a subtlety about the Frenkel-Kontarova model, which you can think of if you take a system where you have two commensurate phases near to each other in one domain wall. And then the question is, does the domain wall know where it wants to be on the lattice? Okay? The phase-on limit, of course, it doesn't know where it wants to be. It can move uniformly. But it turns out that, but that's a bit of a surprise, really, because it's discrete. It's sitting on a lattice, it should know. And there is, in fact, a transition which was described by Aubry a long time ago, which he called the transition by breaking of analyticity, whereby if the interaction strength is big enough, it does pin, right. And if it's not, it's stuck. So does that extend to 2D? Does that affect the superlubricity? And you know, can you actually model it in your case?
So that's a very interesting question. Indeed, I mean, there is, so I guess you're referring to the commensurate to incommensurate transition in these systems?
Well, no, even if it's incommensurate,
right.
It can still be pinned.
It can still be pinned, yeah. So one thing that, one thing that we did is in these systems is we raise the temperature, right? I mean, we're doing these classical simulations, so we can just raise the temperature and ask whether the boundary, which basically would be the solitonic boundary, so to say, whether it actually moves, you know, or whether it diffuses out or what happens to it. It actually does seem to vibrate, you know, it moves as a whole, but it seems to go back and forth as one unit. So it certainly doesn't seem pinned, but that could be, you know, also related to how strong their interlayer potentials and so on, those things are. And these are usually very weak compared to, let's say, the bond strengths in plane, right? Those are the springs that, there's a K by V ratio in some sense, yeah.
I mean, I guess the point is that you can change that simply by pressure.
That is correct, that is correct.
Then there should be a critical point where
it would, that is correct, yeah.
So to continue on this question, basically there is a connection to superlubricity, but you are also calculating the anharmonicity, which should be somewhat related. When the layers become soft, they can adapt themselves, and then the phase-on mode can be gapped. So do you see any connection between anharmonicity and?
So we hadn't analyzed the anharmonicity in that way, but it might be connected. So I mean, this is not, you know, there's also out of plane displacements here in this model, which probably shouldn't make too much of a difference. But you know, at some level, for the boundary to move, there has to be some out of plane displacement which has to follow this this entire thing. So we haven't analyzed it in that sense, but that's an interesting idea. One you know, we could look at it that way and see if there's something. Yeah.
I guess my question is also on the same theme. So I was thinking about why, you know, when we do, let's say, an AFM measurement on something that's twisted at some reasonable angle, it doesn't slide everywhere, right? It looks right. just as happy as it is.
Right.
And I was thinking back to what, maybe I'll say it my experimentalist way, that at the atomic level, the thing is really stuck. So even though there are places where it wants to slide and places it doesn't want to slide.
Yeah, no, but you know, the thing is, I mean, from what I understand from all experimentalists, you never heat your sample afterwards, right? You never heat it because then the angles change and the layers move around. So there could be defects which could be pinning it, or it could be as you know, there could be some reason that these are pinned because of the fact that you know, the potential is deep enough and it sort of stays there. It could be either one, you know, but you know, in our calculations, these modes do come out to where they come out, and they come out pretty naturally.
Yeah, it's a good point, because in TMDs, actually, if you heat them up, nothing much happens. They stay the same way.
I see.
It's very different from graphene.
Yeah, in graphene, for example, if you heat it up, then things move around, and
Yes,
yeah.
right.
So it's not, so it's not clear whether this is related to defects or it's related to something intrinsic between the two layers, it could be either one.
But I wonder if you can look locally at regions which are unstable stacking versus stable stacking.
Right.
Whether one can say something from deformations locally of those
Yeah,
regions.
perhaps, yeah. That's a good point.
Any other questions? Or? If not, then let's thank Manish for this very nice. So we'll have a short tea break now. So we'll meet at 11:45. And as I announced at the beginning of the session, in the afternoon tea break, there's a photo session. So I think maybe Chandni will have more details
afternoon
about
tea break, we'll have a group photo. And one more announcement is regarding a session that we have arranged for today evening. It's at 5:15 after the talks. It's mainly meant for students and postdocs to have an interactive session with some of the speakers. So you could ask questions about anything that you want, basically from postdoc applications to faculty positions, how to apply, or mentoring, or any questions that you may have. So it's meant to be an interactive session. So we'll have that, and after that we'll have the banquet towards the end of the day. Yeah, thank you.
So that's going to be here.
Yeah.